So we're just going to look at some applications of logarithms in the real world. So one of those examples is decibels, which we actually saw in a previous chapter. I'm using a different textbook resource for this. In our previous chapter we had I and IO. Here they've got P, but it's the same thing. So P2 and P1 if you're comparing two different sounds, P and P0 if you're comparing a sound with threshold sound. So remember, this is the formula we saw. L is the difference in the loudness in decibels between two sources. So if you've got one thing that's 20 decibels, another thing that's 23, that L would be 3. P2 and P1 is the ratio of the loudnesses. So one of them is like 3 times louder, 20 times louder, or 100 times louder, something like that. So in this textbook they refer to absolute loudness, being how loud something is relative to threshold sound, which is what we looked at in our textbook. Okay, so in this example, the volume is turned up from 50 decibels to 70 decibels. How much louder is it? So remember I said that this L, that's the difference in the loudness. So that would be 20. That's L is the 70 minus the 50, which is 20. So 20 equals 10 log base 10 P2 over P1. So P1 is the quieter one, 50 decibels. P2 is the louder one, that's 70 decibels. And we're just looking at relatively how much louder one is than the other. So to solve this, we do need to start by dividing each side by that 10. So divide the 10. So 2 equals log base 10 of P2 on P1. And then to undo the log base 10, of course, we do 10 to the power. So 10 to the power of 2 equals 10 to the power of log base 10. So I'm just going to write that over here. So 10 to the power of 2, of course, is 100. Equals 10 to the power of log base 10 cancel out. I've got P2 on P1. So that essentially tells us the answer, but I do like to multiply by the P1. So times P1 times P1. I mean, it's telling us the ratio is 100, so it's 100 times louder. But let's just turn this around. I'm just going to write the P2 first. So it's 100 times P1. So if I get the 50 decibel volume and times it by 100, I would have the 70 decibel volume. So the 70 decibel volume is 100 times louder than the 50 decibel volume. So example 2 asks, what is the loudness of something twice as loud as a 35 decibel sound? So what we're looking for is finding the L, that difference. So the difference in loudness, just be careful that it is the difference in loudness. So a lot of the time people think of it as just the loudness. They get very confused whether that's meant to be the 35 or whatever, but it's actually the difference between the decibels and the two sounds. So 10 log base 10 of P2 on P1. So what they've told us is that the other sound is twice as loud. So P2 is equal to 2 times P1. That's what they're telling us. It's twice as loud. So the ratio of their sounds is double. This ratio is 2. So 10 log base 10. I am going to write 2P1 on P1, but obviously those P1s cancel out. So that's something you can literally just put straight in your calculator, and that comes out to a little over 3. So the difference in loudness is 3 decibels. So therefore, the louder sound is, you've got to add that 3 to the 35, 38 decibels. Another example of something that uses a log scale is the Richter scale that measures earthquakes. So because it uses a log scale, if you had an earthquake with that measured 3 on the Richter scale and one that measured 6 on the Richter scale, a lot of people falsely believe the 6 was twice as intense as the 3, but that's not accurate because it is a log scale. So the formula is quite similar to the decibels one. By the way, I would believe that in an exam they would give you these formulas. You just need to know how to use them. So this is the ratio of the intensity, and this is the measurement on the Richter scale. So A is actually the amplitude of the wave measured. The difference in intensity of two earthquakes can be given with this formula. I used a D there, that was just me, that's the formula uses M's, but just to separate those two. So this is compared to no earthquake, whereas this is two earthquakes in comparison to each other. So in this example, an earthquake measures 5.2 on the Richter scale, and aftershock measures 4.9. How much more intense was the first earthquake? So it's really easy for people to say, oh, that's only slightly more. It's practically the same intensity, the same wavelength would be measured for both. Let's find out. So the difference in their wavelength is 5.2 minus 4.9. So that's 0.3 difference. So our formula is, so notice it's actually the same as the decibels one, but the decibels one has a 10 at the beginning. So A2 on A1, so 0.3 is log base 10 of A2 on A1. Take 10 to the power of each side to cancel out that log base 10. 10 to the power of 0.3 is almost 2. 1.995 equals A2 on A1. So A2 is 1.995 times A1. So the initial earthquake was almost twice as intense. So just that little 0.3 there, and the wavelengths measured are almost double on this one than they are on that one. A third example is the pH scale that is used in chemistry to look at how acidic or basic a solution is. So 0 would be like extreme acid, 14 is like extreme base, 7 is neutral. So like pure water should be around about 7. So the pH is the negative log, base 10, of H+. H+ is the concentration of hydrogen atoms. This is a fairly straightforward example. What's the acidity of a solution with hydrogen atoms with a concentration of 2.3 times 10 to the power of negative 6? Now, this power here is generally going to be pretty close to the answer when it's written in scientific notation. So I'm expecting something pretty close to negative 6, and this is just plugging this number into that formula. So the pH here is equal to negative log base 10 of 2.3 times 10 to the negative 6. And if you put that into your calculator, that is 5.6. So it is acidic. So it's below 7. So it is an acid, not a base. My final example is on octaves in music. So 8 notes make up one octave. So if you started at C, say on a piano, for example, any instrument, you played C, D, E, F, G, A, B, C, you've played one octave. Okay, so there are 8 notes in an octave. The C at this end has twice the frequency of the C at this end. The deeper one is half the higher pitched one. So this is the higher pitch and that's the deeper pitch. So the difference in octaves is log base 2 this time, F2 over F1. So that's just the frequency comparison, the ratio of the frequencies. So here's an example. A note has a frequency of 100 hertz. What's the frequency of a note that is 1 octave higher? So the difference in the octaves would be 1, and that equals log base 2. Now F2 is the higher one, F1 is the lower one, so I'm going to call that X for F2, and F1 is 100 hertz. That's the frequency. So this is slightly different from what we were doing on the other ones. So to solve that, I'm going to go 2 to the power of each side. So 2 to the power of 1, of course, is just 2, and X over 100 times by the 100. So obviously 200 is the answer. 200, and that's measured in hertz. Let's also look at notes that are 2 octaves higher and 3 octaves higher. Now the maths is the same, so I am going to do this through pretty quickly. So 2 equals log base 2 of x on 100. I'm doing 2 to the power, so 2 to the power would be 4 equals x on 100, so times by 100 of course, x equals 400 hertz. So you've seen a pattern now. We had 100 hertz, we went up 1 octave, we got 200 hertz, we went up another octave, and we're now at 400 hertz. So it's doubling each octave. And that's what I said right back at the start, that the C at one end has twice the frequency as the one at the other end. So let's just quickly calculate 3 octaves. So I am expecting double this, I'm expecting 800. So 3 equals log base 2 of x on 100. So 2 to the power of 3 is 8 equals x on 100 times by the 100. X equals 800 hertz. So sure enough, that's what we were expecting. Okay, in this final question, how many octaves higher is a note with a frequency of 4,800 hertz compared with a note of frequency 150 hertz? So we know that the difference in the octaves, I'm just going to use D again, is log base 2 of 4800 over 150. Now 4800 over 150 is equal to 32. So that's log base 2 of 32. Now, there's a couple of ways you can work that out. One is if you already know that 32 is 2 to the power of 5, then we know the answer is just 5. Log base 2 of 2 to the power of 5, the log base 2 and the 2 to the power cancel out, you're just left with the 5. If not, you could also use the change of base rule. So remember the change of base rule, you go log to any base of 32 over log 2. And you can use either log button in your calculator for that. That change of base rule will solve any log like that for you, which is really handy. And that does equal 5. So it's 5 octaves higher.